feed flash vaporization. So in this topic we are going to learn some important aspects about the calculations of total distillates. So we all know about the meaning of total distillates. Basically all the distillates D1, D2, DT, D3, D4, all these distillates, sum of all these distillates are named as the total distillates. And how it can be obtained, basically all these total distillates are in a vapor phase when it is leaving through the flash zone. So the total distillate yield is found by calculating the vaporization of crude which will occur at the condition of temperature and hydrocarbon partial pressure in the flash zone. And how we can get it? So the total vapor, the total distillate that is leaving from the flash zone is basically they have the two terms. One is a feed flash vapor and the second is the material is stripped out from the feed flash liquid. We'll explain about with the help of the diagram about these meanings, how the total distillates are obtained. So that is basically the target of this video. Now before going to the calculations, let us take the one very simple concept of a stripped out fraction, that is SF. So what is a strip out fraction? The fraction of a feed which is stripped out due to the stripping action is called the strip out fractions. For example, in our case, in the bottom section of atmosphere distillation column, a portion of a feed flash liquid is stripped out. This is the feed, this is a liquid of the feed, this one is the liquid of the feed. When it is coming in the bottom section, so because of the steam stripping, because of this steam, what is happening? A portion of this steam is stripped out. This one is called the stripped out vapor. So that is basically what we want to know. So calculate this amount, we can use the stripped out fraction. Let us take some other example. For example, this is a feed, and with the help of steam a portion is stripped out. We can say it is a strip out VSO, vapor, because the strip out is a vapor, and the second, that is the left, is liquid, that is a product. Sorry. So what is happening here? So if suppose SF, we are taking the feed as a F and assuming the SF is the stripped out fraction, that is the vapors. So the amount of strip out VSO, that is VSO. So VSO is nothing but feed multiplied by that strip out fractions. For example, if I say 40% of the feed is vaporized, so strip out fraction is of 0.4. So feed multiplied by the 0.4 is the amount of vapor VSO, and the amount of product, that is the D, is nothing but the 1 minus SF into the feed. So this calculations we require for the in the coming slides. That's why we have given the concept of strip out fractions. Now come to the concept. This is, we all know, this is the bottom section where this is a flash zone. This one is a flash zone. So what is happening here? The feed is entering in the flash zone, that is divided into two parts. One part is the feed flash vapor, the second part is the feed flash liquid. So our target is to find these amounts. How we can do it? So what is happening? This feed flash liquid is coming in the bottom section, and one important thing is that overflash L0, this is also a stream, the liquid stream that is coming above the flash zone into the flash zone. It is coming from above the flash zone into the flash zone, and it is mixed with the liquid, the feed flash liquid. So that net amount will be the overflash plus feed flash liquid. This is the net amount that called the flash zone liquid out. So LOFZ. So this is the amount of liquid that is leaving the flash zone. So what is happening with this liquid? A portion of this liquid is taken out with the help of steam. So this portion is taken out, that is called the strip out vapor VSO, with the help of steam. So what is happening? This vapor and the feed flash vapor, both vapor basically combine together, and that is basically the total amount of the vapor that is leaving from the flash zone. So that is nothing but the total distillate and L0. This is the total amount of the vapor that is leaving, that basically divided into the total distillates and L naught. So this is what is happening in the flash zone. Now let us take the basic material balance around the flash zone. So we know that is the bottom residue, that is a W, that is W. If you see that the W is coming from this way, so this one is a portion where the one liquid is coming, that is LOFZ is coming, and that is divided into the VSO and the W. So W is LOFZ minus VSO, that is a, so but VSO, we can write the VSO as the amount of the basic material, that is the feed multiplied by the SF. So we can write this VSO as in we have explained in this one, in the earlier one, in this one case. So this VSO can be written in terms of their feed. So that's why we can write here LOFZ into SF. Now take the LOFZ common, so LOFZ 1 minus SF. So this is a one step for the bottom. Now come to see about the LOFZ, how this LOFZ is basically is taking part. So if you see, this LOFZ is nothing but that is the feed flash liquid, that is the flash zone liquid leaving. It have two parts. One part is feed flash liquid, this one, and the second part is L naught, that is the flash zone that is coming out. If suppose we assume that total amount of the feed is 100, so this feed flash liquid is nothing but the 100 minus V dash. So this W dash is converted into 100 minus V dash, and that is the L naught is there. And now if you rearrange all these things, if you put LOFZ, LOFZ is nothing but the W upon 1 minus SF. If you put all these values, so what happened, you can take out W is equal to 1 minus, you have to put the value of the LOFZ, 1 minus SF, and then 100 minus V dash plus L naught. So you have to put this value in place of the LOFZ. So we can get W value for this equation. And if rearranging, because our target is to find out the V dash, if we rearrange, we can get V dash is equal to 100 plus L naught minus W upon 1 minus SF. So in this way we can find out this correlation, that is the important one. So V dash is the feed flash vapor. Feed flash vapor can be calculated with the help of the overflash, strip out factor, and the bottom value. So how we can get it? How we can, only the unknown parameter is SF. How we can get the SF value? So this is a graph where we can find out the value of SF. For example, this is the x-axis. X-axis is the steam rate. That is the important thing. The steam rate may be 10. That is a very common value. So 10 pounds of steam per barrel of the stripped liquid. Okay. So if the 10 is given, and you can make the line at the 10 flow rates, 10 pounds of the steam. So if residue is there, that is basically we are going for the reduced crude, that one dotted line, this is for the residue, and you will see it is very slightly above the 20. It can be a say 21 or 20 point something, because very close to 20. So how we can read the y-axis? Y-axis is given in the percentage. So the volume percent of stripper feed out removed by the 100 means if you need to find out the SF value, you have to divide this y-axis by 100. For example, if the y-axis showing the value up to 23.5%, so the SF value will be a 0.235. So in this way we can find out the SF value. So if you put this SF value in this equation, you can find out the other one. If all the other values are given, you can find the V dash. For example, this is the one example where the question is given, basically where yield is given here, and what flash is given here, steam ratio is the steam rate is given here. You have to find out the feed flash vapor. Similarly, the second question is also the same one, where we have given the SF value is 20.25%. you can find out the SF value or the feed flash vapor value. So this is all about this one. We can have multiple questions. For example, derive the feed flash vapor expressions. What do you mean by the steam stripping? Explain with the help of neat diagram. What do you mean by the flash zone? We have discussed all these things. Thank you very much.